Welcome to another lesson where we're investigating probability and applying all those cruel rules, probability rules, to a number of situations where we can start to predict what the chance of certain events are going to take place, what that chance is going to be. Now, remember that we can represent these probability problems using a Venn diagram. That's the focus of what we're going to be doing today. So have a look here. In today's lesson, we're going to focus on Venn diagrams. And in particular, we're going to explore the rules that we've already established, the addition rule, which we also say is the OR rule, the multiplication rule, which we haven't done very much of, which is known as the AND rule. We're going to look at mutually exclusive events, complementary events with the complementary rule, and then we're going to introduce these ideas of independent events and dependent events. So I can't wait to get going. Let's have a look at a Venn diagram. Notice on this classic Venn diagram, we have the sample space represented at S and X that is representing those events that are the favorable ones. Remember to calculate the probability. It's the number of elements of those in X divided by the total number in the sample space. And that's a very important rule for calculating theoretical probability. What else is very nice about this Venn diagram? It introduces to us the idea of those elements that are not in X. In other words, the ones that aren't the favorable outcomes. Do you remember what we call those? Well, have a look. The blue section represents all the elements of the sample space that are not in X. We can say that that is the complement of X. This is equal to not in X. And so the complement is very useful, and we can use it to solve very many different problems using the complementary rule. So please make sure that you understand the complement. There's one other thing that I want to just mention here, is if we look at X and its complement, what do you notice? Is there any intersection? No, you can't be in X and not in X at the same time. So what do you think we would call those two sets, X and not X? Well, they are mutually exclusive. If we've chosen X, we're excluding all those elements that are not in X. That's why we're saying it's mutually exclusive. It's excluding those not in X. I hope that makes sense. So let's just summarize that result. And we can see that in a complementary event, we know that X means that X prime or X dash means not in X. They cannot happen at the same time. And we notice that these are mutually exclusive events. Here's another representation of mutually exclusive events. Here we have two mutually exclusive events, X and Y. Notice that there is no intersection. That the intersection of X and Y, the number of elements in that intersection is 0. And that's why we can say they're not intersecting. There is nothing, if you're in X, you can't be in Y. There is no overlap between these. And that's why we say these are mutually exclusive. Do you remember how we calculate the probability of X or Y when they're mutually exclusive? This is the addition rule, the OR rule for mutually exclusive events. Well, have a look. We recognize that those events are mutually exclusive because there's no intersection, and we can say the OR rule, X or Y, is simply the probability of X plus the probability of Y. So it's the addition rule. So remember that when we have OR, we must remember that we add. And that's very important. Now, we've illustrated that for 2 events. Do you think it will apply for 3 events that are mutually exclusive? Well, have a look at the Venn diagram. There we go. We've got the Venn diagram of X, Y, and Z, and you'll notice that those do not have any overlap in them. There is nothing in X that is in Y, and nothing that's in X that's in Z. So these are mutually exclusive. And for that reason, if we wanted to find the probability of X or Y or Z, okay, all of those, then we would look to see if we could contain all the elements in X or in Y or in Z. It doesn't matter whether they're in X or Y or in Z. We're only worried about that they must at least come from one of those sets. If we were going to calculate that, we would extend the addition rule, and this is what it would look like. Because they're mutually exclusive, notice there's no intersection. Extending the addition rule, it's simply adding those probabilities together. Now, notice when we do that, you can see the scope of the OR is represented by the orange shading. All of those elements. So at least the elements are either in X or in Y or in Z. There are many of them. Don't think that OR is restrictive. OR means more, okay? It means more. It can be in X or in Y or in Z. People get very confused between the OR and the AND, and I want to make that very clear again, that OR means more. Please try and remember that. Now, if we go on and have a look at these sets, recognize first of all that we've got X and Y, and they are intersecting each other. There is a common element in the intersection. So we can immediately say that the intersection of X and Y is not equal to 0. So X and Y in this case are not mutually exclusive. They're not mutually exclusive. And again, if we are going to apply the OR rule, in other words, the addition rule, we need to recognize here that we've got to take into account the intersection. The element that was in X and the element that was in Y would be counted twice. So say, for example, there was a 4 here and a 4 here. If we add those probabilities together, we'll have too much. We have to take away the 4, the probability of the 4 in this one. So it undoes those things and prevents us from counting twice. When we say OR like that, remember we're including everything. And so the picture on the Venn diagram looks like this. Here you can see in the Venn diagram, we've represented all the space shaded in blue. And so this is what we're doing when we ask for the number of elements in X or Y. And this helps us also then to apply the addition rule to calculate the probability of X or Y. In this case, we've only shown 2 sets that are intersecting, but we could add a third set. Look what it looks like. In this case, we've got X, Y, and Z. Notice that we have 4 different types of intersection. In fact, we've got the intersection between X and Y. So that is the intersection between set X and Y. This is the intersection between set Y and Z. And this is the intersection between X and Z. And what do you think this area is representing over there? Well, I'm sure you can figure it out. It is the common intersection of all those sets. It's where there are elements that are common to X, Y, and Z. And so we need to get a picture of these Venn diagrams when we have more than 2 and recognize there is more than 2 different types of intersections. Sometimes it's only the intersection of 2 sets, But there's that third one, the middle one, that's the intersection of all three. And in this way, we can describe it and summarize it as follows. We can recognize that there is an element in the intersection between x, y, between x and z, z and y, and there's an element in the intersection of all three of them. Because of that, these are not mutually exclusive. And that's very important. When we look at these and we say, well, what's the area that represents at least one element in x or y or z? It will be that whole area as represented there. And so we're going to do some investigations to look at establishing from data that has been collected in the field what these intersections could be and what the probability of certain events taking place. These are quite fun, and I'm looking forward to going through some with you. Let's just move on to one other concept. We recognize in this situation that the focus is on the intersection between x and y, and we want to ask about the nature of that intersection. What I need you to understand is that there are two types of events. Events which have an intersection, they are not mutually exclusive. So they're not mutually exclusive. They do have an intersection. In this case, the probability of x does not affect the probability of y. And for these type of independent events, the rule is given that for that intersection, we can calculate the intersection as being the probability of x multiplied by the probability of y. Now guys, this only happens for independent events. It's very important that you understand that the probability of the second event, or the y event, if you like, is not going to be affected by the x. They would be the same sort of calculation. There's no influence of the one on the other. But if there are dependent events, choosing one thing can affect the second one. The outcome of the first event can affect the probability of the second. And those are known as dependent events. And we summarize them very simply as follows, that again, they're not mutually exclusive. There is something in the intersection, but we recognize there's an influence, and this identity doesn't hold. We recognize you can't multiply them together and find what's in the value of the intersection. I think, you know what? It's time for us to do some practical applications of these. And there's some very important rules for dependent and independent events that we're going to discuss as we go further. But please remember, this is part of the multiplication rule. Let's go on. So in this question that we've got two events, A and B. And we're told that the probability of A is 0.48, that the probability of B is 0.26. We're asked to determine what is the probability of A or B if A and B are mutually exclusive. Well, that's a giveaway. I'm sure you've got it. Think about how you would answer the question, and let's get ready to give you the answer. Here we go. So my strategy for answering this question is first of all to look at the Venn diagram. Because I'm told they're mutually exclusive, I recognize that I'm going to draw A and B as disjoint sets. They're not overlapping. There is no intersection. And so what we can say is, if we're wanting to find what is the probability of an element being in A or in B, it's the shaded area in both of those sets. And we recognize, because there's no intersection, that the probability of A or B is equal to the probability of A plus the probability of B. Remember, if they were not mutually exclusive, then we would have to subtract the probability of the intersection. But we can see here, the probability of the intersection is 0 because there's no element in the intersection. And that's how we apply the OR rule, the addition rule for mutually exclusive. Let's do it very quickly. We're going to say it's 0.48 plus 0.26. And if we do that, we'll get that is 0.74 at least. And we have calculated the probability of A or B. Let's have a look at the next part of the question. The next part of the question says that we are asked to find, tricky, the probability of not A and not B if A and B are mutually exclusive. So here it's a little bit tricky because it's the complementary rule. But actually, you know what? It's not so harsh. We just have to take it step by step. And remember, there's more than one way to solve this. So I'm going to do it in one particular way. See if you can find another way. And we'll see if we can get that answer as well. So the way I start this problem is to say, if I'm looking at the probability of A as being given, why don't I find out what the probability of the complement is? And remember, the probability of the complement is 1 minus the probability of A. So in that respect, we can see that this probability of not A is 0.52. And if I were to shade that, I would shade all this area that isn't in A, including B. How about that? I would have to shade B as well. Now, if I recognize that that would cover the whole sample space, notice I'm not covering A, I'm only covering what's not in A. And I've got the probability of not in A. Now, what about B? I'm going to change the color of my pen so we can see it. And we're going to say, what's the probability of not B? Well, that's everything that is not in B. And we're going to recognize that as 1 minus the probability of B. And if we do it, we recognize that that is going to be 0, that's 1 minus 0.26. That's going to be 0.74. Agree? You recognize that if you add those two together, 0.26 plus 0.74, you're going to get 1. And that's the test to make sure that you've got it right. Now, if we were to shade not B on the Venn diagram, notice what I'm doing. I'm going to shade everything that is excluding B, including A. So if I'm going to say, what is the probability of not A and B? Well, that means I've got to find the intersection of not A and not B. So what are the elements that are not in the intersection? Can you see that the things that are common, that have a blue and a red shading on the diagram, those are the things outside of A and outside of B. In other words, it's this area in the sample space that I've indicated here. So it doesn't include A. The overlap, the intersection, is simply the parts that are not in A and not in B. So intersection is what we're looking at here. There is an intersection. We just need to make sure that we're only counting those that are in the intersection. And so I could carry on and do this calculation and apply the AND rule, but there's the shorter way to do it. The shorter way is to say to myself, if I'm wanting the things that are not in A and not in B, then all that I'm going to do is I'm going to say, let's take 1, and I'm going to subtract A, and I'm going to subtract the probability of B from it. So what I'll be left with is the part that is shaded blue and red. I hope you can see that. Now, you can go and test the rule for intersection. Remember, there are common elements, and these are not mutually exclusive. But in the calculation, let's do it quickly so you can get your answer. So we recognize this one was 1, this one was 0.48, and this one was 0.26. So if I recognize what those all add up to, I'm running out of space, so I'm just going to put it over here, up at the top, to get my final answer. And what I'm going to do is I'm going to say I recognize that that is equal to 1 minus a total of 0.74. Okay, that's the total. If I've added 0.48 and 0.26 together, that will give me 0.74, and the complement of that is going to give me 0.26. So there I've got the probability of choosing something that's not in A and not in B. In other words, it's in the sample space. It's not in A, it's one of those unfavorable outcomes. Let's move on. Last question that we're going to do is we were asked to do this and say, if we've got B and A together, we want to find the probability if they're independent events. Now, do you remember what the rule for independent events is? Well, that's right. It's the multiplication rule. So very clearly what we've got to do here is we recognize there's an intersection. Yes, there's the intersection, and that's what we're trying to find. We're going to say the intersection of A and B is equal to the probability of A multiplied by the probability of B, which is equal to 0.48 multiplied by 0.26. Guys, I'm sure you can get your calculators out and check that you've got that. That's what we would do for independent events. I think it's time to take a little break. After the break, we're going to explore some more Venn diagrams. Welcome back, guys. We're going to dive straight into another investigation with Venn diagrams. And this time, we're going to look at a problem that considers 3 different events. In other words, there are going to be intersections of 3 Venn diagrams, 3 separate diagrams intersecting, and we're going to have to do some calculations with that. So let's have a look at it. Here we have a survey that's taken place. There were 50 people in the survey, and they were asked if they'd ever broken the following parts of their body. They'd broken an arm, a leg, or a nose. The following data was established. We had 24 said they'd broken a leg, 16 had broken noses, 5 had broken an arm and a nose. Notice that 10 had not broken any of these body parts, 28 had broken an arm, 9 had broken an arm and a leg, and 6 had broken a nose. We're asked to draw a Venn diagram to determine how many had broken all 3 body parts. Yeah, that's quite a complicated little investigation. But you know what? If we take it one step at a time, we'll make sure that we'll get the answer. So our goal is to find where all three events overlap. I'm going to call the number in all three events x. So let's get going with that. So there we've got set L, set N, and set A. L standing for the leg, N for the nose, and A for the arm. And in the middle of this set, I'm going to say where they all overlap, I'm going to put an X over there. So the people that belong in that set, in that overlap, will have broken a leg, an arm, and a nose. They've broken all three. And that's what we want to try and find. We know that in total there are 50. So let's try and put some data from what was given onto the board here. So we know that the number in the sample set is 50. That's going to become important for us. We recognize that 10 had not broken anything. So there are 10 that sit here in the sample space. They're of those people that didn't break anything. Now, my approach to finding the others is to recognize that if you can look at the intersection of two things, you can add those in quite easily. So we recognize that 5 had broken an arm and a nose. So where we see nose and arm, we can put a 5 into that space. We recognize that 9 had broken an arm and a leg. So an arm and a leg, we're going to put 9 into that space. We recognize 6 had broken a nose and a leg. So nose and leg, we are going to put 6 into that space. Now, can you see what the next steps are going to be? Well, we're going to need to make sure that everything balances. And so we have got to be very careful here to recognize that the totals for each set now add up. And we've got 3 parts of every set. So be careful. You don't go and just enter data wildly. You've got to be thinking as you do it. So let me take you through that. The first thing that I recognize is that the total amount of people that have broken a leg. So remember, guys, this is the people that are in that whole set. That whole set comes to 24. So if I think about it, I would recognize that if they've only broken a leg, then they would sit into this space, okay, into that space there. We have got to recognize all of this adds to 24. But notice that what we've got here is 15 have already been accounted for. So if we take 24 minus 15, that will give us 9 left over. But we've also got to take away the x. So I'm going to say that's 9 minus x for the leg. And in a similar way, I'm going to be able to recognize what's happened for those that have broken a nose. We recognize that there were 16 in total. So all of these numbers add up to 16. Let me change the color of my pen so we can get it very clear. So there's the people that have broken their nose. The number in that sample is 16. We've got to recognize, though, that 11 of them are already counted and X. So what's left over, the people that only broke the nose, is 11. Sorry, not 11. I have made a mistake there. We've got the eraser here, just to erase that. It's 16 minus 11. 16 minus 11 gives us 5. But we've got to subtract X as well. So in this space, we're going to say it's 5 minus X. Wow, that's going to be quite interesting to look at. Let's look at our third set. And again, let's just change the color, and hopefully we can see that as the people that have broken the arm. So we had 28 in this set in total, and what we recognize is that 14 have already been accounted for. There's 9 of them, and there is 5 of them. So what's remaining of those people that only broke their arm must be 28 minus 14, which is 14 minus X, because the minus X is the people that broke an arm, a nose, and a leg. So we've got to make sure that we've set it up like this. Okay, can you see how we're going to be making progress? What do you think the next step is? Well, it's a simple arithmetic problem. In fact, we just have to add everything up and make sure that we get an answer. So let's give ourselves some space, and here we go. And so I've replicated the answer that I've drawn on the board, and I've put it into this arrangement over here. The only thing that I need to make sure that I also have is that I recognize that the number in the sample space is 50, okay? And if the number in the sample space is 50, I can start to add some equations together. I'm going to add everything up and see that I can start to add things up to 50. And if we do that, we'll recognize we've got x in the middle plus, we've got 9 plus 6 plus 9 minus x. That was all in L. And then I'm going to say I've got plus 5 minus x plus 5, and I recognize that that adds up already. I'm not going to add in the 6 because I've added in the 6 already. And I'm then going to say the only things that I've got left that haven't been added is 9 plus 14 minus x plus the 10, and all of this gives me 50. Now, if you add all of that together, what you will find is if you do the calculations, let's get the calculator out. We're going to add all the numbers together. So the 6, 5, and 9, I think you can see 6 and 5 is 15, plus 5 is 20, plus the 10 gives you 30. So we recognize we've got 30 to start with of just the numbers. So we have to add up to 50. So that means that the numbers with the letters all add up to 20. So I'm going to say the following. I'm going to say, I recognize I can make an equation I'm going to make an equation that says the following. 20 is equal to 9 minus x plus 5 minus x plus 14 minus x. Now, if I start adding all the things together, all the numbers together, that's 19 plus 9 is 28. So I'm going to subtract 28 from both sides, and I get 20 minus 28 is equal to minus x plus x minus x minus x. And if I add that together, this gives me minus 8. This will give me minus 2x. And if I then solve for x, I can see that x is going to be 4. How about that? So it was quite a long, tedious calculation. But you know what? It's worthwhile sticking at it and practice these so that you make sure that you're getting them right. Let's see if we can do one more question on this follow-up. So they've asked us to look and see how many people have only broken a leg. Well, you know what? It's not difficult to see. In this case, only broken a leg is in that segment there. It means that we know that x is equal to 4, and we want to find 9 minus x, which is going to be what that is. We want to be able to find out what 9 minus x is. Well, that's simply 9 minus 4, so that's going to be 5. So the people that have only broken a leg would be 5. And so in the same way, you could calculate all the others of those that had only broken one thing. Right. Have a look at this. The probability that a random person that has taken the survey has broken at least one body part. Guys, this terminology, at least one, means that you have to consider all of those that are in the sets the neck, N, L, and A. So it's everything that's in that Venn diagram. except those ones that are in the sample space. Have a look here. So when we're looking at least one, we're considering all of this space. Because even though you've broken 3, you've broken at least one. Even if you've broken 2 of them, you've broken at least one. So all of these are included. The only people that aren't included are those ones that didn't break anything. So the ones that broke at least one is the complement of the intersection in that sense. So what we're going to do is we're going to say that those that have broken at least one is going to be the total number in the sample space, which was 50, and the number that did not break any, was 10. So the ones that are left behind at least one is going to be equal to 50 minus 10, which gives you 40, which is that whole space represented by the Venn diagram. Guys, I hope you can see that there are lots of other questions we could ask, but unfortunately, we need to go for a break. We'll see you after this. Welcome back, guys. We've got a few more activities to get through. So let's not waste any time. Let's get straight to it. Have a look at this question. It says, we're given a list of events. There are 5 events in total, and it's all to do with rolling a dice. And from this list, we need to select a pair of events that are going to be mutually exclusive and complementary. Well, that's quite an interesting thing. So let's just make sure that what we've got here is very clear. So the first thing is, if we were rolling a dice and we got even numbers, well then it would be 2, 4, and 6. If they were rolling odd numbers, then we would recognize that those would be 1, 3, and 5. Now, if we look at just those two, we recognize there's no common intersection between them. If you're an even number, you can't be an odd number. So then we are mutually exclusive. And in the total set, we would recognize there are only 6 possibilities. And so if you're not in the one set, let's call it A, then you would have to be in the second set. And so that was what we mean by mutually exclusive and complementary. But let's have a look at what the Venn diagram looks like. So if we look at A and E as examples, we'd recognize that A was all the even numbers, so we had 2, 4, and 6, and E was all the odd numbers, and we'd recognize those were 1, 3, and 5. Now, we recognize there's no overlap, so we definitely can say they're mutually exclusive. And because they're mutually exclusive, we can apply the addition rule for mutually exclusivity. But we wanted them to be complementary as well. And that means we've got to check that does the probability of A equal to the probability of 1 minus the things that are not in A. That will tell us if they're complementary. Well, if they're not in A, then they're in E. And what we'd recognize then, if we fill in the numbers, we can say that this is 1 minus 3 out of 6, which is a half. So the total is a half. And what do we know about the probability of A? Well, the probability of A is exactly that. It is the total number in A, which is 3, divided by the total number of outcomes is 6, so it's a half. So we can therefore say that these two outcomes, set A and set B, are both mutually exclusive and complementary. Now, you might want to look at those options and recognize that there are others that are mutually exclusive, but they're not necessarily complementary. They don't mean that you can take the two sets and add them up to give you the value of 1. That's what we're looking at when we look at complementary and mutually exclusive. Right, let's move on to our next one. In this case, we're given a less demanding one in a sense. We're saying, let's choose B, which is rolling a 3 or more on a dice. So remember, that's 3, 4, 5, and 6. That's 3 or more. This one, C, says less than 5. So if it's less than 5, then it's 4, 3, 2, and 1. We have to look at the OR rule here. So let's draw a Venn diagram and use that to calculate. I've gone ahead and put some figures on the board already. And remember here, we're looking at the OR rule. We recognize that these are not mutually exclusive. And because they're not mutually exclusive, BC, the probability of B or C, is equal to the probability of B plus the probability of C minus the probability of the intersection of B and C. So if we have to do this calculation, we'd recognize the probability of B is going to be, there are 4 out of 6. So this is 4 out of 6. And the probability of C is also 4 out of 6. Now notice, because we've done that, we've counted the 3 and the 4 twice. So we've got to subtract those in the intersection. And that's what I'm going to do here. We recognize that the intersection has 2 elements out of the 6, so we subtract those. And if we get the totals there, we recognize this is going to be 8 out of 6 minus 2 out of 6, which gives you 6 out of 6. And that's exactly what we're hoping to get, because all the elements in the sample space exist within the combination. And so the probability of getting B or C is 100%. Very good. Now, the last thing we're going to ask ourselves is, are these events independent? And we have to be careful when we're doing this independent calculation. So let's just make sure that we've got the calculation over here. We recognize where the sets are, and we want to make sure that we're going to calculate the probability of B and C. Now, what's the probability of B and C? Well, it's this here. We can recognize the probability of B and C. We calculated it over here. It's 2 out of 6, which is 1/3. And what we recognize is that we have got 1/3 as the intersection. Now, if they're independent, then what we should be able to do is to recognize that the probability of B multiplied by the probability of C is going to be equal to 1/3. But is that the case? Well, let's have a look and see. So if we take the probability of B, recognize the probability of B from that calculation over there is 1/3. We take a look at the probability of C, recognize that's 1/3. Now, what's the product of those two? If we say multiply them together, that's 1/3 multiplied by 1/3. Can you see that's going to give us 1/9? And in the intersection, we only had 1/3. So these are not independent events. That's the test. We can recognize that these are not independent events. Right, guys, I think that's more or less brought us to the end of our questions. Let's just do a quick sum up. In today's lesson, we've looked at the fact that you can use Venn diagrams to represent 2 or more events. We've also spoken about complementary events, where we've recognized that to find the complement of something, the complement of A is equal to 1 minus the probability of A, the probability of the complement. We've also recognized mutually exclusive events. Remember, there is no intersection, the intersection, the number of elements in the intersection is equal to 0, and we're going to use the OR rule here. For independent events, we're going to use the multiplication rule. Guys, I hope you've got a good idea now of more tools in your toolbox, and you're in a better position to predict what the chance of a future event taking place will be. From me, goodbye.